Differentiability is another way of saying that we can find the derivative of a function. We just learned that the derivative of a function is a limit, a two-sided limit of the difference quotient. So differentiability means that that two-sided limit of the difference quotient for a function exists. Now let's revisit the idea of continuity. Continuity in simple terms is a function that is easy to draw without lifting up your pencil. Now we're going to combine those two ideas. If a function is differentiable, then it is also continuous. Remember that if a function is differentiable, then we can find the derivative using that two-sided limit definition of the difference quotient. So if we assume this, then what I'm saying is we can conclude this. So what we're going to do is start with this equality that comes straight from the definition of continuity. I'll take the left-hand side, and then I'm going to do some math magic to the left-hand side so that we can arrive at the right-hand side. So we're going to start here. We'll do some math magic with the assumption that f is differentiable, and then we should end here. So over on the right-hand side of the screen, we have the left-hand side of our equality. The first thing that I'm going to do to that is add and subtract f with a plugged into it. Now if you look at what I have in red right there, those two terms add together to be 0. So it's essentially the same thing as just adding 0 to our function. Doesn't change anything, so that's a legal move. Next, I'm going to multiply by x minus a and divide by x minus a. Remember that any number divided by itself is equal to 1, and multiplying by 1 doesn't change the value of anything. So right here, where I'm multiplying and dividing by x minus a, that's the same thing as multiplying by 1. So again, legal math move, not doing anything illegal here. Now I'm multiplying that ratio, x minus a divided by x minus a, only to the first two terms, f of x minus f of a. And the reason for that is because I want to use my assumption that f is differentiable. So I'm trying to build that statement kind of by adding and subtracting or multiplying and dividing. If I just shift my terms around, I can see that I have that difference quotient, f of x minus f of a divided by x minus a. So I'm taking that top group of terms and then the x minus a, and I'm putting them into their own difference quotient. Then I'm putting the x minus a into its own limit, separating them by multiplication. And then I'm also using a limit law for this addition, where I'm adding f at a, so that that term gets its own limit as well. Now from here, we're going to apply the assumption that our function is in fact differentiable, which means that what I have in this first term, the limit as x approaches a for this difference quotient, that's the same thing as the slope of the tangent line, or the derivative with a plugged into it. This next term, the limit as x approaches a for x minus a, that just says let all the x's turn into a's, and if I did that, this would be 0. So I'm taking the limit of a constant 0, and I'm multiplying those two terms there. And then lastly, I'm just going to bring down that limit as x approaches a for our function f at a. So what we're left with then is the slope of our tangent line times 0 plus the limit as x approaches a of f at a. Now anything times 0 is 0, so this whole first term goes away. Then I'm just left with the limit of a constant. Notice that f with a plugged into it, there's no x's left. All of the x's already turned into a. So what I have inside of that box doesn't change even though x is changing and turning into a. So that would just be f at a, which is exactly what we wanted to get at the end, the right-hand side of our limit. Not our limit, of our equation. So we started with the left-hand side of that equation that we wanted to conclude. We made the assumption that f was in fact differentiable right here, where we took that box out and replaced it with the slope of the tangent line, and then we continued until we got to the right-hand side of our equality. So in plain terms, what we just said is that a derivative exists if the two-sided limit exists. That was our assumption. And if the derivative exists, we can now conclude that the function is also continuous. And this is great because if you think about it, to define continuity before, we checked 3 separate conditions. And now we're saying just check to see if the function's differentiable. And if it is, then you know that it's also continuous. Now, does that work in reverse? Good question. We just said if it is differentiable, then we know that it's also continuous. But what if we flip that? If a function's continuous, do we know that it's also differentiable? Well, let's investigate. I'm looking at the function absolute value x. And just by looking at it, we can tell it's continuous. There's no missing pieces. We can trace over this with our pencil without having to lift anything up. So we know it's continuous. Now we want to ask, is it differentiable? To answer that question, we just need to find out if that two-sided limit exists. If this two-sided limit exists, then we can say yes, the function's differentiable. If it does not exist, then the answer would be no, it is not differentiable. So let's check to see if that limit exists. I'm going to go through and replace the f of x with absolute value x and f of a with absolute value a. And then I notice that I've got an indeterminate form. If I try and replace all of the x's with a's, I get 0 over 0. So we need to separate this so that we can actually evaluate the limit. And one thing that we'll need to remember is that the absolute value function can be written in a piecewise form, where it's equal to x if x is positive, and it's equal to opposite x if x is negative. And it doesn't matter where you put the equality. You just have to switch your definition at some point. So I said equals goes with the negative one, but it doesn't matter. So that means to find this limit, we're going to have to split this into a left and a right side. So our goal is to show that this two-sided limit does or does not exist. And to do that, we need to find the left-sided limit and the right-sided limit. If we're allowing x to approach the origin, because this is where we might have some weird stuff going on, if we allow x to go towards 0 from the left, then we're on this side of the line. Our definition for absolute value x in that case would be negative x, and then absolute value a, that would be the absolute value of 0. I'll go ahead and write that out. And then on bottom we would have x minus 0. We can clean that up a little bit. X is approaching 0 from the left. We have negative x on top and x on bottom. Now, as x is approaching 0 from the left, this fraction, negative x over x, actually simplifies to be negative 1. So even though here we have an indeterminate form, we can simplify that down to be -1. The limit of a constant where x is approaching 0 is still just that constant. So we found the limit on the left is approaching -1. Now, looking at the picture, you might think, no, that's approaching 0. You're right. This is the derivative. So this is saying that from the left side, the derivative of f at 0 looks like -1. And I think we would agree with that. Looking at this line, it looks like it has a slope of -1. Now let's check the right side. For the right-sided limit, x is approaching 0 from the right. The absolute value of x would be replaced with just positive x, and then minus absolute value of 0 over x minus 0. We can clean that up. We have x over x. This is an indeterminate form, so we have to simplify before we can finish. X divided by x is equal to 1. Any number divided by itself is equal to 1. So the right-sided limit is equal to +1. This is saying that the derivative appears to be equal to +1 from the right side. And if we look at the left and the right side by side, we can see that they are not equal to each other. Coming from the left, we have a rate of change or a slope of -1. And then from the right, it looks like we're on a slope of +1. This function is differentiable everywhere except for at x equals 0. Any function, in fact, that has a sharp corner like the absolute value function is not differentiable. And that's because at this corner, the derivative changes rapid fast. It goes from -1 to +1 in the blink of an eye, maybe even faster. Now, to show that something's not differentiable, all we did was try to calculate the derivative using the limit definition. In this case, we had to separate it into a left and a right-sided limit. We showed that those two limits don't agree with each other, which means the two-sided limit does not exist. But more important than that process is that we now know that just because a function is continuous does not mean that we get to assume that it's also differentiable. It could be continuous, but if it has corners, it is not differentiable. Here's another suspicious function. It's the cube root of x. Now we can see that it's continuous, we can tell that there's no corners, but we want to know, is this function differentiable? The only place that I really have any suspicion, again, is right here at the origin. So let's see if we can find the limit, the two-sided limit, as x approaches 0 for our function. Replacing g of x with the definition, cube root x, and g of 0 with cube root 0. We're really trying to show this two-sided limit either does or does not exist. Now, we know the cube root of 0 is just 0, so I'm going to simplify that and just write minus. We don't even need to write -0. And then in the denominator, x minus 0 is just x. So we've simplified our difference quotient to just be cube root x divided by x. If I plug in 0 here for x, I do get an indeterminate form, so we need to try and simplify this further. Now, if you're thinking there's a radical there, let's use the conjugate. Hold on a second. I need two terms to be able to do a conjugate. I don't have a second term here. So conjugate's not the way to go, but instead, maybe we can do some simplification. The cube root x can also be written as x to the 1/3 power. And then we have x on bottom. And remember that if you have x to the m power divided by x to the n power, then we can simplify that to be x raised to the m minus n power. So that's exactly what we'll do here. We can write x to the 1/3 minus 1 because the denominator, that x has an exponent of 1, even though we don't see it. That would leave us with x to the negative 2/3. So instead of writing the limit where x approaches 0 for cube root x over x, we're going to write it as 1 over x to the 2/3. That's the same thing as negative 2/3. Remember, x to the negative n is the same thing as 1 over x to the positive n. So these are a few algebra things that hopefully we remember. Now when I go to apply this limit, remember I want the two-sided limit to exist. I notice that I have a fixed number on top, 1, but on bottom x is getting tiny, 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 turning into 0. And anytime I have a number divided by 0, that's going to blow up to infinity or negative infinity. And although we can say that a limit goes infinite, in this case, if we were to try and talk about the rate of change or the derivative, we would be saying that it doesn't exist as a finite number, it's infinite, which is a bit of a problem because the derivative blows up to infinity too fast. The same way that in a corner, the derivative switched to a different value in the blink of an eye, this derivative would turn infinite in the blink of an eye. So another case for derivatives to not exist is anywhere that you might have a vertical tangent line. So corners are not differentiable, neither are vertical lines. One more function. This is called Uncontrollable Oscillation, which to me sounds like a health disorder. But basically, this function, x times sine of 1 over x, squiggles back and forth so fast that the derivative never has a chance to settle down onto a particular value. What that means is if I try to find the derivative of this function, and it specifically has the problem around 0 again, so let's let x approach 0 for our function h of x. Then we're trying to prove this two-sided limit either does or does not exist. I can replace h of x with the function's definition. So I'll write x times sine 1 over x. And I know to use this portion of the piecewise because if x is approaching 0, then x is not already at 0. So if I'm saying let's go to 0, then I'm not already there, right? Let's go to the mall. If I was already at the mall, you'd be upset with me for inviting you late. So we know to use this definition, not this one, for our two-sided limit, where x is approaching 0. If I plug 0 in to my function h, then I would use this bottom piece. So my h of x is here, minus h with 0 plugged in, that's just 0. And then on bottom I have x minus 0. I don't need the minus zeros in here, that's overkill. Notice that I have a factor of x in the numerator and denominator, so I can divide those guys off. That just leaves me with sine of 1 over x. If I plug 0 into this, that's almost like saying sine of infinity. Now remember that the sine function oscillates back and forth. So I can plug in very, very large values into sine. That's not the problem. The problem is this does not equal a fixed number. It's constantly changing. As infinity gets bigger and bigger, the value sine of infinity is squiggling around because it's an oscillating function. So we can't find the derivative for this function because it oscillates uncontrollably. So now we know 3 different situations that are not differentiable: corners, vertical lines, and uncontrollable oscillation. We have one last thing to talk about, and that is higher order derivatives. So remember that the derivative of a function we just found is actually a derivative. So if I start with some function f of x, then I can create a derivative like f prime of x. And since this is a function, we can find the derivative of that. If I take the derivative a second time, then I'm just going to add a second prime. One way to write that, which is a little bit strange, but it's f prime of x inside parentheses with another prime outside of it. You can stack the double primes this way if you want, or you can use an entirely different notation where instead of using primes, we use d dx. So if I'm starting with a function f of x, the first derivative looks like d dx of f of x, which we can also write as df dx. And again, that's a function. The derivative is a function, which means we can take the derivative again of that derivative, and we would write that as d squared f over dx squared. So this is saying I've taken the derivative twice. And in fact, we can keep going. There's no reason to stop at f double prime. There's no reason to stop at d2f dx squared. We could take this and keep going f triple prime. We can go to the fourth derivative, fifth derivative, as far as you want. In fact, the farthest we can go is a generalized f to the n. That's saying I've taken the derivative n times. And n could be any integer you want. Same with this other notation. Instead of using d2, we could do a third derivative. We could do that to the fourth power, to the fifth power, as far as we want. Notice that what looks like exponents in the numerator on the d and on the x in the denominator, those match. They're the same number, and they tell you the order of derivative that you've taken. And again, we could do this to the nth derivative. That would look like dn dxn. Let's try one. So if I have the function 2x squared minus 3x plus 1, then the first derivative looks like the limit as h approaches 0 for f of x plus h minus f of x all over h. I need to find out what f of x plus h looks like. That's going to take every x and replace it with x plus h in parentheses. And I'm going to clean this up the best I can before we go forward. Multiply out that perfect square binomial. Distribute the minus 3 into the parentheses. Keep track of that negative symbol. Now I'll distribute the 2 into that trinomial in the first term. And then I'll check to see if anything simplifies. And it doesn't appear that there's any like terms. Everything's a little bit different, so that's the best we can do. Let's go ahead and plug that into the difference quotient. So that is f at x plus h. Now we need minus f of x. Make sure to put parentheses around that, so we're subtracting the entire f of x function. All of that is divided by h. Now here's where we're going to go through and simplify the best we can. Remember that with this version of the difference quotient limit, anything that doesn't have an h in it should be subtracted off. So when I distribute this negative into the function back here, I can drop the parentheses and change all of the signs. So that becomes minus 2x, that becomes plus 3x, and then minus 1 after I've distributed the negative. Then I can see the positive 2x squared and the minus 2x squared, they cancel off. The minus 3x and the positive 3x, they cancel off. The plus 1 and the minus 1, they cancel off. So let's copy down what we have, clean it up a little. If I plug h equals 0 in, I will have an indeterminate form, so we need to simplify this. Notice that there is a factor of h in every one of the terms in the numerator. So if we factor h out, we would be left with h times negative 4x plus 2 minus 3. And that's still divided by h from our denominator. Our h's will divide off, so really we're looking at the limit where h goes to 0 of negative 4x plus 2 minus 3. When we plug h equals 0 in, oh, I dropped an h, look, 2h squared, this should still have one factor of h. So that should be, when I plug h equals 0 in, this term goes to 0, I'm left with minus 4x minus 3. That is our first derivative. So to find the second derivative, we need to find the derivative of the first derivative. So let's copy down what our first derivative is. F prime of x is equal to negative 4x minus 3. Now I'm going to erase everything we have on the screen, but repeat the process for this new function. Okay, to find our first derivative, we used this definition. To find our second derivative, we're just going to add an extra prime here so that we're looking for f double prime. And then inside of this limit, instead of using the original function f, we need to use the derivative function f prime. So we need to find f prime with x plus h plugged into it, where we remember f prime is negative 4x minus 3. So that would look like negative 4 times x plus h minus 3. We can clean that up a little bit by distributing the 4 in. There's no terms that we can combine, so that's as simple as it gets. Let's go ahead and plug that into our difference quotient. And then we can subtract the derivative function inside of parentheses. And then pop that on top of h. When we distribute our negative, it becomes a plus 4x plus 3, and we can drop the parentheses. The minus 4x and the plus 4x cancel each other out. The minus 3 and the plus 3 cancel each other out. I'm left with negative 4 times h divided by h. The h's divide each other off. I'm really just looking at the limit of negative 4, which is a constant. It does not matter where h is going. Negative 4 is equal to negative 4 all day. This is our second derivative. So we found for the function f of x, which was 2x squared minus 3x plus 1. The first derivative, f prime, was equal to negative 4x minus 3. And the second derivative was equal to negative 4. And we can match that up with the other notation. So df dx, that's the same as this right here. That came from taking the derivative of the function f of x. And then our second derivative, that's d2f over dx squared, that came from taking the derivative of our derivative. It was the second derivative.